All right, welcome back. In the previous lecture, we learned how to calculate the forces on surfaces that are immersed in a liquid. And we learned how to do a calculation of the force on a flat surface. And we also learned how to do the calculation of the force on a curved surface. So what I want to do at the beginning of today's lecture is show you how to do a practical calculation of finding the force on a curved surface. And I picked this example where we have a liquid in a tank, and the free surface of the liquid is right here. And then this side of the tank has this wall that has this interesting shape. So there is first a section of the wall that is straight, and we know the depth of the water in that straight section up to the point where the curved portion of the wall begins, and that depth is h. And then this segment of the wall is curved, and is curved in a circular path. And we know that the radius of that circle is obviously just a quarter of a circle. The radius of that quarter of a circle is capital R. And suppose we want to calculate the force that the liquid exerts on the curved portion of the surface. And as we learned last time, the way we do this is we actually find the two components of the surface, of the force, the two components of the force separately. So we find the horizontal and the vertical components of the force separately. Recall when we're calculating the force on a flat surface, we go ahead and find the total force with its direction, because in that case, in the case of a flat surface, it is very easy because the force is always perpendicular to the surface. So here we're going to split the problem. So if we look at the surface again in a little bit more detail, the curved surface, obviously for me to find the total force, I will have to end up doing some integration over the entire curved surface. But if we look at only an element of that surface that I have highlighted here in this schematic, and then I have the differential force dF that acts normal to that portion of the surface, and I have decomposed that force, that differential force, into two components, the horizontal one that I call dF sub h, and the vertical one that I call dF sub v. And I'm going to set out then to find those two forces separately. So here is another schematic of the same portion of the wall, except that I have zoomed in to see exactly what is going on. In fact, I might want to zoom in a little bit more here, where I can see the portion of the surface, which of course, since I am zooming in and this is a differential segment, I have represented it as a little flat segment of length ds. And here's the same forces that I showed in the previous schematic. So I have my differential force dF in blue, and then the components of that force in the horizontal and vertical directions, dFH and dFV. And I also show this angle theta, which is the angle that the differential force makes with the horizontal. And then another thing that I have done is I have also decomposed my ds into a vertical and a horizontal components of that segment, and I call them dy, the vertical one, and dx, the horizontal one. And of course, the angle theta is also shown in that figure. So from what we've learned before, I can compute the differential of the vertical force by simply multiplying df times the sine of theta. And I know that the differential force is the pressure that is acting at that point times the differential area. And the differential area, of course, is ds. And I'm using 1 because I'm doing the calculation for 1 unit of depth into the paper. or the width, if you want to call it, the width of this surface into the paper is a unit 1. So this part of the expression is just the differential force, is the pressure times the differential area. And then the sine of theta from the black triangle is just dx divided by ds. What that does is that cancels the ds on both sides, and I am left with pdx. Times 1, of course, the unit width, but we don't need to keep dragging that along. And now I can compute the pressure at that depth as the product of gamma, or density times the gravity, the acceleration of gravity, times z, which is the depth to that point. And if I simply plug in that into my previous expression, then I find that the differential of the vertical force is rho gz dx. And you can see in this diagram what is meant by z. As I said, is the depth z to the point on the surface, the differential element of the surface that I am considering. Now, of course, this quantity that we see here on the right-hand side of this expression, z dx, is times 1, again times 1 because it's unit width. So z times 1 times dx is nothing but the volume that I have shaded here in blue on this right-hand side figure. And of course, that is really the differential volume of liquid that is sitting on top of my differential surface. The only difference being this little amount of volume that you see here. I'm going to zoom in on this one schematic a little bit. The only thing that I have left out is this little volume, which is triangular in the limit, that I have left out of the calculation. But of course, that would be negligible in comparison with the dV that you see in blue. So I can really, to the approximation that we're taking the limit as the differential s goes to 0, this volume represented by the product of z and dx is really the volume of liquid that is sitting above that differential surface. And therefore, since that is the volume, and if we multiply that times the density, we get in the differential mass in this volume, and then of course times gravity, what we are getting as a result is that once we integrate over the entire surface, is that the vertical component of the force is, zoom out a little bit, the weight of the fluid sitting above the surface. We learned that already in the previous lecture, but we want to plug in the numbers for this specific case. So that is done right here. So if I now look at the entire portion of the surface, which you see here, this curved surface is the one that we're interested in computing the force on. Then I have again shaded in blue the entire volume of the fluid that is sitting above the surface. And you should notice how I put above between quotes, because we know that in reality there is no fluid in this region. The fluid is to the left of the surface, but the way the calculation works out, because we're interested in the pressure at that depth, and that is irrelevant as far as whether it's one side or the other side, assuming that the surface has very negligible thickness, then that's why we say is the weight of the fluid above the surface, where we put the above in quotes, because that applies also to the cases in which there is no fluid above the surface. But it's like if there were fluid above the surface. So that volume is represented here in the square brackets. And of course, that volume would be the volume of the rectangular region represented by H times capital R, again times 1 unit of width. And then the volume of the quarter of a circle part of this volume, which is pi r squared over 4 times the unit width, that being the volume and then times rg to make it the weight. So that's how we compute the vertical force, or the vertical component of the force on a curved surface. And in this particular example, those would be the results. All you need to do to finish a problem like this, of course, is just to plug in the actual values if you're given data for these quantities. So how do we compute the horizontal force? Well, we do the same thing. So we go back in reference to this diagram. In reference to the same diagram, now we're interested in computing the horizontal force, the FH. And the only difference, of course, is that instead of the sine, we have the cosine. And so it's dF cosine theta. So dF cosine theta, the cosine of theta is now dy over ds. So everything is pretty much the same, except that now you have a dy instead of a dx. So again, the differential force is the pressure times the area, which is P times ds times 1. So the end result is that the differential force in the horizontal direction is now P dy. And of course, if I now integrate this over the entire surface, then from what we learned earlier about calculating the force on flat surfaces, this integration dy will go over the entire projection of the curved surface. So if you want to put the result in words, what you're really doing is you're computing the horizontal force, or the horizontal component of the force, as the force on the vertical projection of the curved surface. This is illustrated in this figure. So there is my curved surface that I am computing the force on, and the result that I obtained just above is telling me that to find the horizontal component of the force, all I need to do is project this curved surface onto a vertical plane. So if I make a projection of this curved surface on a vertical plane, I get this so-called vertical projection. So to find the horizontal component of the force, all I need to do is find the force that would act on such a vertical surface. And if we plug in the values, then of course we know that to find the force on a flat surface, in this case it happens to be a vertical surface, then all we need is the pressure at the centroid of that surface times the area of that surface. And I call it A sub v to remind ourselves that this is the vertical projection of that area. So the centroid of this area, of course, this projected area is a rectangle, again. And it's a rectangle that measures r in the vertical direction and measures 1 in width into the paper. So this is the right-hand side here. R times 1 is the area of this rectangle. And the centroid of such a figure, such a rectangle, of course, is measured from the surface of the liquid. And that centroid then is located at h plus r over 2, because the centroid, of course, is in the middle, is at r over 2, but we must not forget that we need the pressure there, so therefore we have to measure the distance to the centroid from the surface of the water, and that's why this h gets added. So it's really h plus r over 2 is the total depth to the centroid, and then of course times rho and times g to get the pressure. So the pressure at the centroid is rho g times h plus r over 2, and the area is r times 1. If we just get rid of the 1, then we get an expression there for the horizontal component of the force. So that's how we find the vertical and horizontal components of the force on a curved surface. And I did the calculation for a surface that doesn't have a three-dimensionality to it. Right? It's simply, we did it per unit depth. But if it happens to be a surface that, that is curved in two directions, so not only this curvature, but maybe there's also a curvature of the surface perpendicular to the plane, then the results are easily extended to that. They don't really change. You're still computing the vertical force as the weight of the fluid above the surface, and the horizontal force as the force on the projected surface. So even though the calculation is two-dimensional, the extension to three-dimensional is analogous. Okay, so the next topic that I want to cover today is to show you how to calculate the so-called buoyancy force on a object that is completely immersed in a liquid. So here I drew an arbitrary shape object at certain depth under the surface of the water. And the purpose of the exercise is to find the so-called buoyancy force. That is the force that the liquid will exert on this object, and we all know from experience that this will be a vertical force that will tend to push the object upwards. And so whether the object is actually pushed up or continues to sink or even stay in place will depend, of course, on a force balance that will include this buoyancy force that we're going to calculate and the weight of the object at the very least. So the way to find this buoyancy force is really an extension of what we just did. So best way to look at this is to do the following. You can take this object and split it into two parts. So if I think of this object, this entire object, and I put a couple of points here. So if I take the leftmost extreme of this object and the rightmost extreme of this object, and I imagine that I can cut the surface that contains this object at those two places, then I have this surface and I have this bottom surface. So I split it into two surfaces. And again, I am doing it as if it were a two-dimensional object, but the extension to three dimensions is trivial. It doesn't really change any of the results. And so if I do that and I apply what I learned in the previous example and in the previous lecture to finding the vertical force that is acting on these two surfaces, I already know that for this upper side of the object, the force that is exerted by the liquid is equal to the weight of the liquid that is sitting above that surface. So I shaded this liquid in blue, and if I compute the weight of that liquid, then that gives me the force that I'm calling now F1, which is the one acting on the top half of this object. And then I do the same thing for the bottom half of the object. I know that the force that this liquid is exerting on this surface is drawn here, is F2, is a vertical force, because the liquid, of course, is on the bottom. But from what we learned, that force F2 is equal to the weight of the fluid above the surface. And remember, the above was in quotes, because we know, of course, that there is no fluid inside the object. But for the calculation of the force, it is as if there were fluid inside the object. So we just need to find out that entire volume that sits above that surface, and I call that V2. And that gives me my vertical force acting on the bottom half. So of course, to put the two things together, what I need to do to find my buoyancy force is to take F2 and then subtract F1 from it. I know that F2 is larger because there is more volume above this surface than there is above that one. So I already know that the force will be upwards because F2 is larger. So if I simply subtract them, F2 minus F1, then I find that is density of the fluid times gravity times the difference in the two volumes. And of course, the difference in these two volumes is nothing but the volume of the object itself, of the body that is in the water or in the liquid. So the bottom line is that this buoyancy force, which I obtained by subtracting the two forces, is nothing but the density of the fluid times gravity times the volume of the body, of the submerged body. And of course, we refer to that as the weight of the displaced fluid, because that would be the weight of the fluid that is displaced by this object when it is put into the liquid. And that's the way you calculate the buoyancy force. Again, if you want to do a force balance to see whether this object will rise or will sink, then the other force that you need to include is the weight of the body. And of course, the weight of the body will be an expression very similar to this one, except that it will be the density of the object, the density of the body. So it's really the difference in densities that will determine whether the body rises or sinks. All right. So one more item in today's lecture will be the calculation of the rigid body motion of a fluid. So everything that we have done to this point involves fluids that are at rest. Right? All the hydrostatic calculations that we just finished involve fluids that are not moving. So as we gear towards analyzing the flow of moving fluids, because that's of course what is more interesting, then the next step would be to consider what we call rigid body motion. And of course that means that now this fluid, in this case we'll be looking at a liquid, is moving as if it were a rigid body. So that means it is not deforming. It's like just moving as one solid piece. And of course there is only a limited number of problems that we can look at to consider rigid body motion, but one very simple one, and it's typically the first example that you see when you're looking at fluid rigid body motion, is this one. Imagine that you have a tank and it's sitting on wheels, and there is a liquid in it, and if this tank is at rest, then we know that that surface is horizontal. But the question is, what happens if this tank is not at rest, but is actually accelerating to the right with a certain constant acceleration A, in the presence of a gravitational field, which in this case, as we would normally do, will be pointing in the negative z direction. That's why I have a unit vector here, k, to remind me that's the positive z direction upwards, and g is pointing in the negative z direction. So this is our problem. And our goal is to see what happens to this liquid as the tank moves to the right with an acceleration A. In particular, I would be interested in knowing what will happen to this free surface, right, to the surface that separates the liquid from the air outside. Our starting point has to be, again, Newton's second law. So we derived this earlier, which is nothing but the sum of forces and the acceleration of the element. And remember, when we derived this equation, we were looking at an infinitesimal element of fluid. And I have indicated that in green there. There is a little square here in green. And that's my differential element of fluid that I am thinking of when I'm writing this equation. Remember, this equation represents Newton's second law per unit volume of that differential element. So I have a term, the negative of the pressure gradient, which represents the forces per unit volume acting on this element due to the fact that there is a pressure field around that element. Then we have the weight of the element, again per unit volume. So it's just density times gravity. And we, of course, know that that's in the negative k direction. So I've already included the direction of this vector by putting that minus k in there. And then the right-hand side, which is in Newton's law what would have ma, but since we're doing it per unit volume, is rho a, is the density times the acceleration. So that's my Newton's second law equation per unit volume for a fluid element. So what I need to do is, of course, indicate the direction of my acceleration. So as I said at the beginning, the tank is going to be moving to the right. Let's make that the x direction, to the right. And therefore, the acceleration of the tank is just the magnitude of the acceleration times the unit vector in the x direction, which is I. And then go ahead and take this vector equation and break it down into components. And so we see that here. I have a horizontal component in x, a vertical component, well, the vertical component is the last one. A vertical component in z, and then this one in the middle is the component of this equation in the direction perpendicular to the paper. That, of course, doesn't have any meaning in this problem because there's nothing going on in that direction. So the important one, of course, are the first and third. So the component of the pressure gradient in the x direction is partial p partial x. The component of the pressure gradient in the y direction is partial p partial y, and the component of the pressure gradient in the z direction is partial p partial z. And then as far as the weight is concerned, it only appears in the last equation. I have moved it to the right-hand side, so the sign is positive and it's rho g. There is nothing in the y direction because there is no weight in the y direction, and there is no acceleration in the y direction, so there is a 0 here. And then in the x direction, of course, I have the rho a term. So the acceleration of the tank only appears in the x direction, and the weight of the fluid only appears in the z direction. So these are my three equations. And essentially what they're doing for me is they're telling me the three components of the pressure gradient in each of the coordinate directions. And since they're telling me that there is no pressure gradient in the y direction, I already know that there's no change in pressure in the y direction. So one thing that I conclude right away from these three equations is that the pressure is only a function of x and z. It's not a function of y because of the middle equation. So if that is the case, then I can write, remember from differential calculus, I can write the exact differential of pressure, dP, which by definition of an exact differential, in this case in 2 dimensions, it would be dP dx times dx plus partial p partial z dz. And of course what I do is that I have those contributions to the exact differential, dP dx and dP dz, because I have them from these previous equations. So if I just plug them in, I plug that dP dx is minus rho a, and I plug in that partial p partial z is minus rho g, then I get that expression that you see right there. So that is really a very important result, because now I have an expression that tells me how much the pressure changes if a pressure changes by an amount dP, if I move an infinitesimal amount in my flow field. So if I move a short distance from one point to another, I will be moving a certain dx and a certain dz. This tells me how much the pressure will change. So going back to one of our original goals, what if we want to find the location or the position or the orientation of our interface, or the so-called free surface, which is where the water meets the air, or where the liquid meets the air, the surrounding gas. And there is only one thing that you need to know. If there is a condition that describes that surface, what is that condition? Well, that condition is that the pressure is the same all along that free surface, because that would be, for example, the pressure that exists in the gas that is outside the tank. Let's say, for example, that's air. If there is air surrounding this whole experiment, then the pressure of that air is given and is a constant. So I identify the free surface as the location where the pressure doesn't change. In fact, that's true for any constant pressure surface. So if I look at, again, this last equation, that gives me the change in pressure, any constant pressure surface will be one in which dP is equal to 0. And that includes, of course, the free surface. So if I set that to 0. So if I take the previous equation and I set the pressure to 0, I get this. So this equation now then will tell me what is the orientation of the lines along which the pressure is constant. So if I simply solve for that, dz over dx is minus a over g. That is nothing but the slope of those lines. I can integrate it if I want to find actually the equation of those lines. So if I integrate this, I get a constant minus a over g times x. And of course, those are straight lines. They are straight lines, and they have a negative slope, which is equal to minus a over g. What does that mean? That these lines, these constant pressure lines, look like this. They are straight lines with negative slope, and of course they're all parallel to each other depending on the value of the constant. So since all constant pressure lines are straight lines with negative slope, that means that also the free surface is a straight line with a negative slope. So if I want to answer the original question, well, I might say this is what it might look like, where the uppermost line here, let's make it a little thicker, represents the free surface. So we put our little triangle there to denote the free surface. That's what the liquid would look like. That's what the shape it would take if the tank is moving to the right with a constant acceleration a. Of course, you can then elaborate on the problem. You can ask yourself a few more things if you have a few more pieces of information. For example, you could try to find out if the water is going to spill. So if you knew how high the walls of this tank are, then you could determine by a few extra calculations whether the water in the tank is going to remain in the tank or if it's going to spill out. And that is the last portion of this lecture. So when we come back, the next lectures we're going to begin talking about fluid dynamics. Thank you.